This is a short video lecture for Chapter 2, Science, Matter, Energy, and Systems. On your screen is a list of key terms pertaining to the chapter. Please look over this list and be certain that when you're reading, these terms are becoming familiar to you. What do scientists do? Science is a search for order in nature. Scientists use observations, experiments, and models to answer questions about how nature works. Scientific theories and laws are the most important results of science. The goal of a scientist is to develop theories and laws based on facts and data that explain how the physical world works. A hypothesis is a possible and testable explanation of the data. A scientific theory has been tested widely and is supported by extensive evidence and is accepted as being a useful explanation of some phenomenon by most scientists in a particular field. A scientific law is a well-tested and widely accepted description of events or actions that we find happening repeatedly in the same way. Scientific laws cannot be broken except by discovering new data that lead to changes in the law. Critical thinking is the ability to distinguish between our beliefs and knowledge, i.e., opinion and fact, or separating judgment from facts. One of the chief tools of a good scientist is to have critical thinking skills. All of you will need to sharpen your critical thinking skills during this class in order to understand sound scientific and technical work in an objective and unbiased manner. Consider this while doing your team research project this semester. A couple key steps for critical thinking are to gather all the information and don't mistake ignorance for perspective, and learn all you can about the topic before you make a decision on it. Understand all the terms and definitions that you will use in relation to a topic and that others use as well. Question how the information was derived. Was the information from scientific studies? Was there a control group or an experimental group? Has the study been repeated successfully? Question the source of the information. Is the source vested in the outcome of the issue? Is the source biased? Do underlying assumptions affect the viewpoint of the source? Question the conclusions. Do the facts support the conclusions? And examine the big picture. Study the whole topic. Look for hidden causes and effects. During this class, we will have different topics that we're going to look at that are considered to be complex issues, and some of you may already have opinions on those issues, but it's important to look for the facts, and without the facts, it's all opinion. As mentioned earlier, scientists are curious, skeptical, and demand evidence. Sometimes when new data is being presented on a particular topic or issue, scientists can be skeptical of that. They want to make sure that the data and the conclusions being drawn from the data are truly verifiable, sound science. Often, what we do in the field of science is we have a peer review process. In order for scientists to publish their experiments and their results, peer review scientists will review those experiments and results and approve or disprove them in terms of being verifiable, accurate scientific experimentation. The peer review process allows other scientists to look at the methods that were used, review the results of the experiment, consider the reasoning behind the hypothesis, and confirm that the data is sound and unbiased. Being human, scientists are not free from bias, but a peer review helps to reduce personal bias and allows scientific work to be published in journals that are verifiable, reputable, and based on good sound science. The results of science can be reliable, unreliable, or even tentative. Reliable science is when the data, the hypothesis, the models and the theories and the laws are widely accepted by other scientists in the same field. Unreliable science, or what I call junk science, has not been rigorously peer-reviewed or has been discarded as a result of a peer review, or perhaps was even put out into public information despite a peer review disproving of it because it has biasness in it. And tentative science is not widely tested or accepted science. Let's shift topics and talk about matter and what it consists of. Matter has mass and takes up space as either a solid, gas, or a liquid. There are two chemical forms, either elements, where it consists of all the same atoms, or compounds, where it consists of a combination of more than one type of atom. Chemical elements that you will read about in this book are listed on your screen. Arsenic, lead, mercury are metals that you're going to learn about. And there's some inorganic compounds listed there as well as chlorine and fluorine. Elements cannot be chemically broken down into simpler forms. They're usually represented on the periodic chart with a 1 or 2 letter symbol as depicted on your screen in the top right corner. Molecules are when two or more atoms of either the same or different elements are held together by chemical bonds. Depicted on the screen in front of you is a water molecule that consists of 2 hydrogen atoms and 1 oxygen atom, as well as a carbon dioxide molecule that consists of 1 carbon atom and 2 oxygen atoms, and then there's a methane molecule on the far right which consists of 1 carbon atom and 4 hydrogen atoms. A term that you should be familiar with is ions. They are a group of atoms with 1 or more net positive or net negative charge. Ions used in this book are listed on the screen in front of you. The hydrogen ion has a positive charge. The sodium ion has a positive charge, as well as the calcium ion, aluminum, and ammonium. Negative ions are also listed, such as the chloride, hydroxide, nitrate, carbonate, sulfate, and phosphate ion. Compounds that you may read about in your textbook this semester are also listed on the screen on the left side. Sodium chloride, sodium hydroxide. You will definitely hear about carbon monoxide and carbon dioxide. You'll often hear me refer to NOx, NOx, and that's nitrogen oxides, nitrogen dioxides, and nitrous oxides. Also listed are methane, glucose, hydrogen sulfide, sulfur dioxide, and there's 2 acids listed, sulfuric acid and nitric acid, as well as ammonia and calcium carbonate. Organic compounds have at least 2 carbon atoms and combine with various other elements, most commonly hydrogen. The only exception to this rule is methane. Methane consists of 1 carbon atom with 4 hydrogens, and it's because it's the simplest organic compound. Also, methane is a more potent greenhouse gas than carbon dioxide. Organic compounds are classified into families, and one family I'd like to point out is the hydrocarbon family. This is when you have carbon and hydrogen atoms bonded together, and sometimes you can add a halogen known as chloride, fluoride, or bromide, or maybe an oxygen. When we're looking at just carbon and hydrogen atoms, these are found naturally as crude oil and natural gas. And we take this natural material and we refine it into fuel oil, gasoline, and jet fuel. When you take organic compounds, carbon and hydrogen, and combine it with a halogen, such as bromide, fluoride, or chlorine, you then have what's called a chlorinated or fluorinated hydrocarbon. These are hydrocarbons with halogens. An example of a hydrocarbon with halogens is trichloroethylene, or TCE. It's a common contaminant in leachate from landfills. It's also a cleaning solvent and a dry cleaning treatment. TCE has been documented as being carcinogenic, meaning it can cause cancer. So it's an organic compound that we actually regulate and keep an eye on in regards to its use, its storage, and its disposal. Another example of a hydrocarbon is ethylene dibromide, or EDB. This is a compound additive to gasoline to guard against engine knocking in our automobiles. Another example of a hydrocarbon is chlorofluorocarbons, or CFCs. These are used in Freon for refrigeration, and when released into the air, the CFCs can have an adverse effect on the ozone layer in our atmosphere. This is an example of the chemical reaction that occurs when we burn coal in a coal burning power plant. The solid carbon in the coal combines with oxygen gas, represented by the O2 symbol, and then it reacts to form a gaseous compound of carbon dioxide plus energy. When we burn coal, heat is the energy that is released, and then we use that heat to superheat up water to create steam to spin a turbine to generate more electricity. So this is an example of a chemical reaction. Okay, so now let's switch gears and talk about a couple scientific laws. The first one is the law of conservation of matter, which simply states that physical or chemical changes can take place in a chemical reaction, but no atoms are created or destroyed in the process. Also, energy changes are governed by the law of thermodynamics. The first law of thermodynamics, also known as the law of conservation of energy, basically states that we cannot get more energy out of a physical or chemical change than what was actually put in. The second law of thermodynamics basically states that when energy is changed from one form to another, it always goes from a more useful to a less useful form. This slide is just another way to word the two laws of thermodynamics. Let's talk about two forms of energy, kinetic energy first, and then potential energy. Energy is defined as the capacity to do work or transfer heat. Kinetic energy is energy associated with motion. Wind and flowing water are good examples of kinetic energy. Heat is also a form of kinetic energy. When two objects at different temperatures contact one another, heat flows from the warmer to the cooler object. Also, radioactive or electromagnetic radiation is a form of kinetic energy that occurs when energy travels as waves as a result of changes in electrical and magnetic fields. Potential energy is stored energy, such as water stored behind a dam and the chemical bonds in gasoline. Potential energy can be changed to kinetic energy, such as releasing water from behind a dam can spin a turbine to create electricity, or the burning of gasoline in a car. The pictures on the screen in front of you are of a hydroelectric dam that was built in China. It's called the Three Gorges Dam. It is the world's largest hydropower project and the most notorious dam. The massive project set records for the number of people displaced, more than 1.2 million, the number of cities flooded, 13 cities, 140 towns, 1,350 villages, and the length of the reservoir, more than 600 kilometers. The dam is 1.4 miles long and 607 feet tall, and it's 5 times bigger than the United States Hoover Dam. This is a good example of taking potential energy and converting it to kinetic energy and generating electricity as a result. The location of the Three Gorges Dam is depicted on the picture on the bottom right corner of your screen. We'll talk more about this dam in later lectures.